Lesson 2 is going to be about properties of ionic, covalent, and metallic bonds. So we're going to be analyzing the different types of intermolecular forces, and we're going to start with ionic bonds. So some atoms are more stable when they gain or lose an electron, or possibly two, and form ions. This results in a full outermost electron shell and makes them energetically more stable. Now, because the number of electrons does not equal the number of protons, each ion has an electrostatic charge and attraction. We just learned this from video lesson 1. So let's talk about ionic bonds. An ionic bond is a transfer of electrons from a metal to a nonmetal in order for both atoms to obtain a full valence shell, which is stability. Whenever this occurs, the metal is giving up one electron, or two, or three, depending on its charge, to a more reactive non-metal. Whenever we use an ionic bond, the metal ions are always going to be first in the name and in the chemical formula.
So the formation of ions is the first step in forming an ionic bond. Sodium atoms, or the metal atoms, will always lose electrons to their non-metal counterparts, which will always gain electrons.
Because they're more electronegative.
Right. Now, the attraction between the opposite charges pulls them together, which then creates the formation of an ionic compound. So some of the properties of ionic compounds is that they're hard crystalline structures. They can be dissolved in a solution to form the ions that make the ionic bond. And they can conduct an electric current only when in aqueous or molten or liquid state. And they have high melting and high boiling points.
So when we look at pure water on the far left-hand side with a conductivity tester, all what a conductivity tester is an apparatus used to tell scientists if the solution allows a current to go through it. When you look at the distilled water on the far left-hand side, because there are no positive or negative ions, electricity cannot flow through it. Even though in the middle we're using a pure ionic compound, you're noticing that the positive and negative charges are fixed in a solid. Because of that, they cannot run a current. But on the far right-hand side with the illuminated conductivity tester, we're noticing that when you take an ionic compound and dissolve it in water, its ions break apart from each other, allowing for them to be attracted to either the positive or negative electrode in the conductivity tester. That is what we call an electrolyte. And an electrolyte, in any aqueous solution, these compounds are now free-moving ions, which allow the flow of electrons to produce an electrical current, as indicated in the light bulb circuit test shown above.
Covalent bonds, or molecular bonds, are a chemical bond that involve the sharing of a pair of electrons between two nonmetals. These electron pairs are known as shared pairs or bonding pairs. For many molecules, the sharing of electrons allows each atom to attain the equivalent of a full outer shell, corresponding to a stable electronic configuration.
Don't forget, guys, covalent bonds are only between nonmetals, and hydrogen is a nonmetal. So if you see things like HCl, that's a covalent bond. So here are some examples of covalent bonds. You're noticing that there's going to be a sharing of the two. If you notice in our top left example for the hydrogen, that's following the duet rule because it only needs 2 electrons to be satisfied. And if you're noticing on the far right-hand side for our carbon and the 4 hydrogens, they themselves, the hydrogens, are being satisfied by the duet rule, but carbon, because it has 8 dots around it, is being satisfied by the octet rule.
So in an ionic bond, they're more pulled together like 2 magnets. In a covalent bond, they're physically sharing those electrons. So in order to see carbon that has 8 electrons, just follow carbon's outer circle and count how many electrons are on that circle. You see that there's 8. In hydrogen, count how many electrons on its outer circle, and you'll see each hydrogen has 2.
So covalent molecules are going to be soft. So a lot of covalent things are going to be either in the liquid or gas phase. Even if they are a solid, they're going to be things like plastic, which is very bendable and flexible. All covalent molecules have a very low melting and boiling point, which is some of the reasons why they're either liquids or gases at room temperature. Covalent molecules, because they don't have a charge or an ion, do not conduct electricity.
Metallic bonds are the attractive forces metal atoms of a particular metallic element has between themselves via this sea of mobile electrons. Think of it as they're freely floating electrons. They're not necessarily attracted to just one nucleus, they're attracted to any nucleus that's in their surrounding area. Instead of orbiting their respective metal atoms, they form this sea of electrons that surrounds the positively charged atomic nuclei of the interacting metal ions. The electrons then move freely throughout the space between the atomic nuclei.
All metals have metallic bonds. So if you're using potassium, it has metallic bonds with itself. That means all the potassium atoms in your sample are freely sharing all of their valence electrons with one another. And these are some of the reasons why metals are going to be very conductive, very shiny, or malleable, because they can easily bend or absorb energy. So again, with the metallic sea of electrons, the electrons are not bound to any particular atom, thus they can flow all around. Because they can flow and move around the sample, that gives metal the ability to be very, very, very conductive for both heat and electricity.
So the properties of metals, it's really just this fact that they have this sea of mobile electrons. So the reason why metals conduct heat, the reason why they are conducting electricity, why they're malleable or ductile, they don't dissolve, they have very high melting boiling points. This all revolves around the idea of the fact that they have a sea of mobile electrons, freely floating electrons.
So in class, we're going to be asking you guys all the time to analyze a bond to recognize if it's a ionic, covalent, or metallic bond. The first way to do this is when you look at your compound to always analyze the very first element. If you look at the first element and it's a metal, you can always be guaranteed that it's going to be an ionic bond. Okay? So if you look at the second element, PCl3, phosphorus, not potassium. Phosphorus is a nonmetal, and it's with chlorine, so we can tell it's covalent. In the third example, we have gold by itself. So if you have a clump of gold, how is gold sticking to gold? Gold is sticking to gold via metallic bonds. In the fourth example, between hydrogen and oxygen, you have a covalent bond. Fifth example, you have copper and chlorine. That means it's an ionic bond. The sixth example, what happens if you have a sample of pure titanium? How is titanium sticking to titanium? Via metallic bonds. The seventh example, you have potassium and chlorine, but it's aqueous. That just means it's in the dissolved phase. That means it's also ionic. And now we have two atoms of oxygen stuck together. We call that a covalent bond.
So remember, metal, nonmetal, ionic, metal, metallic, nonmetal, nonmetal, covalent.